Alright, in this video we will go over binomial or Bernoulli distributions as well as Poisson distribution. So the binomial, aka the Bernoulli distribution, is used for discrete probability distribution, and it gives just two possible values, the success and failure. So kind of think of it as like a coin flip if we get heads or tails. Usually we can see this as like dummy variables. If we're trying to land, if the success and failure values are often given by 0 or 1. This is the formula of the CDF function for the Bernoulli distribution. So the summation, if we're trying to find the probability of this specific value of x being equal or less than the value, then we're given by the summation of y starting from 0 to the max value of x, or the x floor, of the binomial coefficient from starting from n, and then y representing the number of successes. And then this formula right over here is what we use to determine that. I kind of circled it over the formula, so let me circle that again. Okay, well, I still circled over the formula, but the point is we don't usually calculate this whole formula by hand because it's very long and tedious. So it's that binomial coefficient times the probability that is given, powered by the number of successes that we want, times 1 minus the probability, so the probability of not getting the result, powered by the number of failures, which can be seen as the number of trials minus the number of successes. Alright, so let's quickly go to the example. So let's say a basketball player is shooting 6 free throws, and his or her chance of making it is 0.7 or 70%. And so if we want to find a chance of the player scoring 4 or fewer, we can write that as the probability of x being equal or less than 4 of sigma y equals 0, 4 being the floor of the beta coefficient of shooting 6 times, and the success is 4. Again, finding this by hand is we're using this function right here, which is, we don't want to really do this by hand unless if you're asked to, which in most cases you won't be. But the probability of success, which is 0.7 of making the free throw, we want to find a chance of the player making it 4 times or fewer, times probability of failure, and the number of failures, which if he makes 4 or fewer, if he makes exactly 4, then he'll miss 2, and we're finding the cumulative. So we're using the summation notation because we're essentially finding like the probability of the player making 1 and 2 and 3 and 4. So that's why we're kind of like adding all the probability up. So when I said we're not going to do this by hand, I'm saying that because we can just use a Bernoulli table. Now, unfortunately, just from my limitations of the recording, I'm not able to access a Bernoulli table right now. But usually, if you look at the table, I think the most important thing is you have to use a cumulative, because that's what we're utilizing right now. If it says 4 or fewer, so usually there will be like the number of samples or trials, and then like right next to it, there will be a number of successes. And then for the horizontal, it's given by the percentage. So like 0.1 and then like 0.9 over here. It should be fairly straightforward as long as you know what the variables are standing for. So I'm not gonna go explicitly over how you can find a probability. I think you can kind of figure that out. Anyone can figure it out for themselves. All right, for the second example, let's say we want to find the probability of the player making at least 4 out of 7. So the player is shooting 7 this time, and the player wants to make at least 4. Okay, so if we want to find the probability of the player making at least 4, again, if we're utilizing the cumulative distribution function, we want to set the notation in terms of less than. So in this example, how can we kind of say that the chance of the player making at least 4 out of 7 in terms of like equal or less than is? Well, it turns out that the probability of the player making at least 4 is actually the probability of the player making equal or less than 3, because if we let's say the player makes exactly 4, then we're essentially saying the player misses exactly 3. And then if the player makes over 4, then if the player makes more than 4, then the player has to miss less than 3. Obviously, greater than 4 and less than 3 aren't the exact probability. Hold on just a second. Okay. So the probability of a player making greater than 4, again, we can't utilize this greater than function, so we say it in a different way. We say the probability of 1 minus the probability of the player making equal or less than 3. And then so mathematically we can say that we can rewrite the formula given up above once again, even though we're not going to calculate it, but I think it's still useful to get an intuitive sense from the formula. So this formula I wrote is based off here, not the original question, because we're subtracting it from 1 afterwards. So this can be written as, through some space. Okay. So this can be rewritten as 1 minus, if you use the Bernoulli table for this part right here, you'll get 0.0126. And this is the result if you subtract it from 1. So again, the player has a fairly high chance of making at least 4 out of 7, given that there's a 70% chance of making each shot, which again intuitively makes sense. I think if I were to re-explain this part right here, again, we can't utilize the greater than or equal to sign, so we have to convert it into less than or equal to, which is why I did 1 minus the probability of x being less or equal to 3. So we just have to like kind of translate if it asks for something, a probability of greater than something or at least, then we have to kind of like translate into a less than or a sign. All right, finally, what is the chance of the player making exactly 5 out of the 7? So again, if we write that in a mathematical notation or mathematical formula, we can actually write that as the probability of x being the shot being less than or equal to 5 minus the probability of the shot being equal or less than 4, because that is the difference and we're trying to find the exact probability. So for the distribution function or the cumulative distribution function, you can just subtract this from this. They should be right above and below each other. So 671 minus 0.353 equals 0.318. So a fairly low chance of the player making exactly 5 out of the 7, which makes sense because there's a very good chance that the player will make, 4 out of 7, 6 out of 7, 7 out of 7. And then note that you can also use an exact probability. There's also a Bernoulli distribution table for an exact probability, but for the sake of consistency, we'll use the cumulative function table. And then again, some useful characteristics. The mu of the binomial distribution is given as just the sample size times the probability of success. So in this case, 0.7 times 7 or 6. We'll just say 7. And then the variance, which is 7 times minus 7.3. I don't have that on my notes, so I'm just going to calculate that real quick. Okay. 1.47. Okay, so for now, for the Poisson distribution, the definition is given by a discrete probability distribution, like the binomial distribution, and it measures the number of events occurring in a given time. So the key phrase is a given time period, because that's why we use the Poisson distributions. It's measuring the frequency within the given time and given the average number of occurrences in the time period. This is the function right here. So lambda powered by x times e to the power minus lambda all over x factorial. So obviously x factorial means like if it's 5 factorial, then we would multiply by all consecutive lower values. Again, we rarely well, that's not true. We do often calculate this by hand, but in the real world, you would usually do this on the software. So lambda is represented by the average rate of the event occurrence, and x is given by the number of events we are trying to find. A cool and simple feature of this Poisson distribution is that the mu is actually equal to the lambda, and the variance, once again, it equals to lambda. So both the mu and variance is also the same. All right, so for the final example, let's say an employee averages 5 phone calls a day or an hour, and we want to find the chance of the employee receiving exactly 3 phone calls. All right, so copying this formula right here, probability of the employee receiving equal or less than 3 phone calls. The problem said exactly 3 phone calls. Okay. All right, the probability of an employee receiving exactly 3 phone calls is given by 5. So total number of average rate of occurrence powered by 3. The number of occurrences we're trying to find. times e to the power of minus 5. So lambda stays consistent all over the x factorial. Again, x is given by 3. I'm not going to calculate the exact probability of this. Intuitively, I would probably guess around, find a chance of the employee receiving exactly 3 phone calls. Probably around like 30%, just off straight gut instincts, but I have no idea. All right, and then if we want to find the Poisson distribution, so like if we want to find the probability of like employee receiving equal or less than 3 phone calls, then we would use a Bernoulli Poisson distribution table. Same for the exact probability. We all there's tables for both. So if you want to save time, it's not the smartest to use the formula. Not the smartest to use the formula given up here. All right, that is all for the binomial and Poisson distribution. In the next video, we will go over confidence intervals.